Welcome everyone. This will be the part 7 of CUDA programming series, and in this particular video we will be talking about performance and how to manage the DRAM or global memory access when you are writing your CUDA kernels. So the goal is to understand how we can bridge the performance gap between the GPU processing cores as well as which is called the off-chip global memory, which is called DRAM. So the GPU comes with a DRAM, which we also call global memory. Before that, what you need to understand, there is a memory bottleneck always. In every sort of processing unit, you will see. For example, in CPU, you have registers, L1, L2, L3 cache, RAM, and disk memory. The access from RAM is slow and the access from disk is the slowest. Same goes for a GPU. The access from DRAM or the global memory is the slowest one. So what you need to understand is a GPU has thousands of cores. These are processing cores, and these are super fast cores that work together to solve a particular computation problem. But consider it like this. So all of these workers or cores in our GPU, they access something from DRAM or the global memory, and they have limited number of docks or channels for that. Or so let's say this is our DRAM. There will be limited number of docks where we can access this memory from, right? Now, if the cores they are constantly waiting for memory access to arrive from the DRAM, the output of the GPU will be much slower no matter how fast they are, however we parallelize them, how much we can increase the parallelism, it won't increase, it is not efficient. So what we need to understand is something called memory coalescing. This is the core and the most important part of this video. Now, why is a DRAM slow? So a DRAM is made up of multiple cells. You can think of them as capacitors which hold charge. There are multiple sensors whose job is to check these charge and understand whether there is a threshold, and are these capacitors which have these charge, are the values of this charge above a certain threshold. If it is, can it be considered 1 or 0, like switched on or switched off? And there are multiple number of these sensors, so the latency of access from DRAM is pretty much higher because of this stuff. So consider it like this. There is a capacitor that is trying to charge some sort of a wire, and a single access and along with the sensor checks takes around a nanosecond, let's say. Whereas while we are in a GPU, the cores operate in sub nanoseconds. Even if it is zero point 0.1 nanosecond, there is a 10x slower or 10x slow speed that we are observing in this case. Now, to compensate, how DRAM works is, so the DRAM is designed to be efficient when we read a chunk of consecutive data from it. So suppose you design your kernel such a way that consecutive threads in a warp. So this is a warp. It will have threads all the way from T0 to T31. So this is a 32 group threads, right? All of these threads access consecutive locations in the memory. So let's say T0 access X, then the next one access X plus 1, then the last one access X plus 31. So these are consecutive locations in the global memory. So the hardware recognizes this pattern, and it understands that you require consecutive locations from the memory. So it combines all of those individual read or access operations into one single one, and it is called a DRAM burst. So it sends all of these locations at once to the warp instead of doing it one by one. right? So the analogy for this is, consider you are going to a library, and instead of going to the library again and again to fetch one single book, you get 10 books at once or 32 books at once, saving your time, right? Now, what exactly is memory coalescing? So the GPU hardware's ability is to combine multiple individual memory request or access request from the group of threads, which is called a warp, into a single large burst, a DRAM burst. So just to write it again, so we will have multiple memory request. Hardware recognizes that if it is consecutive memory request in the group of 32, it will send the or complete the request in something called DRAM burst, where it will recognize and send the data back. So when we have a thread in a warp, so a group of 32 threads, and they are trying to access consecutive locations in the memory, the hardware will coalesce these 32 small requests into a big request, right? Now, how will you achieve coalescing? Let's say it comes, all of it comes down to calculating a memory index. Suppose we are in C where we have some 2D arrays of, let's say, nm dimensions. And in C, the arrays are stored in row major order. So row 1 will be stored like this, then row 2, then row 3, and so on, row up to n rows, right? And all of the m elements of each row will be stored one by one in linear order. Now, suppose if we are uh, indexing m k times width plus column, or in this case, k times m plus column name, how will this work is the column is calculated, let's say, as block id x dot x times block dimension dot x plus thread idx dot x, right? And if we are in a warp, if we are in a warp, our 2D warp is laid in such a way that thread idx dot y component remains constant for all the threads in a warp. Only the thread idx dot y changes, dot x changes, sorry. So for consecutive threads, what will happen is k will remain constant for a thread. For thread 0, the let's say it is 0, then for the next thread we will access this element, and so on. For the 32nd thread we will do this. Now you will observe in the global memory all of these are consecutive locations, right? So hardware will recognize this pattern and send all of the required data at once in a DRAM burst. So just to summarize again, k and width, they are same for all the threads in a warp, right? But column changes according to thread idx dot x. And we are accessing consecutive memory locations based on this. Now, if instead we are accessing something called this sort of index, column times m plus k. Now again, k and m are constants. Now column will vary accordingly. So we will start from all the way 0 and go to 31. So the first thread will access m uh, k. Second one will access m plus k. Third one will access 2m plus k, and so on. So you will observe that all of these elements in the global memory are at a distance of m with each other. So these are not consecutive memory locations. So first thread is accessing something from here. Then we have a gap of m. Then thread 2 comes in here, access this cell. Then we again have a gap of m. Then thread 3 accesses this particular location in the global memory at a distance of m. These are not consecutive locations. These are not like this. They have a distance of m between them, which the hardware sees that, okay, this is not consecutive memory locations that the user is trying to access. So what it will do, it will not send a DRAM burst, and this will in turn slow your kernel. So these will be sequential requests, and all of these will be individual requests instead of combined in a one single big request. Will it be possible to combine it in a big request? No, because no consecutive memory locations are in this case. So this will cause some sort of a traffic jam while accessing things from global memory. Now, there's a technique called corner turning. So when you this is something of a clever technique to handle the cases where your access pattern is naturally uncoalesced. So like accessing when you are accessing columns in a row major matrix, right? When you have a row major matrices, but you are trying to access columns, this is naturally uncoalesced access of a data. So the problem is we need to compute, let's say, a tile of matrix, right? And it is stored in a column major order. And if we load these tiles in the registers directly, it will be uncoalesced and slow because we are indexing it something like this, n dot columns plus k, right? So the solution is to use a shared memory. We have discussed what shared memory is in the earlier videos. So the goal is in shared memory, we will load coalesced data in a coalesced pattern, obviously, and access uncoalesced. And this will be faster because we are directly accessing from the shared memory instead of the global memory. And as you know, the access of shared memory is faster, and all of the threads in a particular block have access to the shared memory, right? So just to summarize, what exactly is coalescing? So we are combining the request of memory access from threads in a particular warp into a single transaction or operation where they can access consecutive memory locations. It is important to use efficiently use the DRAM's burst capability, and we should try to avoiding overwhelming the memory bus of a DRAM. And if we are trying to do this, we can use something called corner turning using shared memory. Now, uh, the problem is even with coalescing, memory request will take some sort of a time. So the bus, if you can say so, the bus of reading the access from the memory is efficient, but it is still takes time to return it back to the GPU, right? So how do you keep your cores busy during that time? You have to keep a lot of work ready to go. So how it works is there are channels. So there are independent memory controllers. So these are like different channels coming from DRAM and GPU. Then we have banks. Each of the channel is connected to multiple banks of our DRAM. Then we have, yeah, I guess that is fine. So you just the modern kernel writing process abstracts away a lot of these details, but you need to understand basically that you need to keep your memory access patterns coalesce together. Nothing else is important than understanding that fact. Now, we have discussed earlier what is occupancy. So it is the ratio of active warps in a SM to the maximum number of possible warps or threads. So we have occupancy is the ratio of active threads in a SM divided by maximum number of possible threads, right? When we are writing a kernel, it is very important for us to check that whether we are achieving high occupancy or not, because the GPU parallelism is expensive, and we need to make sure that whatever operation or kernel that we are writing, it uses it to the fullest of its capabilities. Now, warp issues a memory load instruction, let's say, and this will take hundreds of cycles, right? So instead of stalling, the SMs, the each of the SM has a warp scheduler. So let's say we have warp A, it is waiting for some operation to complete or a memory access operation from DRAM to complete, and it will take some sort of time, multiple cycles of a GPU, right? In the meantime, warp scheduler will schedule warp B or warp C, which are ready to do their operation, ready to perform their arithmetics, right? and they will finish their operation, and meanwhile warp A has finished the required memory access from global memory and it can continue again. So you will see, instead of waiting for warp A to compute, finish the operations, the warp scheduler has scheduled for warp B and warp C to finish their operations. In the meanwhile, the warp A and the data for it has arrived from the memory and it is ready to continue now, right? So high occupancy is very crucial for hiding the memory latency. The warp scheduler will always try to schedule a large pool of ready to run warps, and it ensures that whenever the compute cores are always busy, instead of waiting for some other warps to wait for the data, right, from global memory to arrive. What else we can understand in this? Now, what we also need to make sure is we don't fall for unnecessary uh, memory coalescing, or let's say coarse factor. Let me tell you about coarse factor, what it is. So right now we have seen examples of a thread working on one single element. Instead, we can design a kernel like this. It can work at 2 or 3 or 4 elements at once, right? This is called coercing of threads. So suppose you have but it works in only certain amount of cases. Suppose you have a simple vector addition. This is not compute heavy. You cannot do coercing in this case because you're just overdoing it, and we might not be able to create enough threads for the block to keep the entire GPU busy, right? This will in turn reduce the high level parallelism of a GPU and can hurt the performance. So also you need to understand that a coercent thread where we are accessing 2 or 3 elements or changing the 2 or 3 elements of the output uh, object or output array, let's say, at once, we will require too many registers for one thread, right? And in that case, you have to also consider whether our streaming multiprocessor is capable of handling those threads for all the warps and threads that are currently active. So just to summarize, thread coercing is a technique where we access multiple elements of the output and change it. It also provides some sort of a trade-off where we can reuse the data, but we potentially risk using or losing some sort of data parallelism from the GPU, and it can also result in lower occupancy. Suppose you have one register per thread, right? And now you are accessing 4 different elements. Now you have 5 registers per thread, and you now have to check the SM's hardware configuration if it can allow 5 registers per thread for all the threads that are currently active. If it is not possible, it will reduce the number of threads that are active, and in turn, we will lose the occupancy. But our goal was to increase the occupancy as high as possible. So you need to take care of that as well. So the checklist, there is a performance checklist described in the PMPP book. You can go through it, but just to summarize it, our goal is to maximize the occupancy, try to increase it. Why? Because we need to hide latency. We need to check for coalesced access from the global memory. We need to minimize the control divergence in a warp at least. If we are reusing a lot of data, use tiling and shared memory. If it if a kernel is particularly compute heavy or we have enough registers to take care of, we can definitely look at thread coarsening, but it is something that you should check. You should profile your kernels after doing thread coercing and understand whether it is degrading your performance or not, and if it is, remove that from your kernel. So the bottleneck that we identified is they are the resources that are limiting your performance, right? What we need to make sure that our arithmetic units are 100% busy, or basically as close to 100% as possible. And if our arithmetic units that are doing all of the compute work, they are often idle. Are they waiting for the data to arrive? Or if they are, then we can focus on tiling or coalescing or trying to increase our occupancy, right? Okay, that is it in terms of theory. Now, how will it work in a real kernel? Let's see some examples. So this is a simple kernel. This was a problem for from lead GPU. So what we have here is we are trying to do a matrix transpose where we have an input and output matrix. So we have input matrix of n by m dimension and output matrix of m by n dimension. So the goal is the j comma ith element of output will be equal to, I hope you may have guessed it, input I comma j, right? So first we are identifying the indices that we need to change or swap with each other. So I will be calculated using y. This is a standard convention in CUDA. Then we have jth index calculated using the x part of all the block dimension, idx and thread. And then we are, since we have a row measure format in CUDA, the jth comma I element of output is calculated as j times number of columns, which is n plus I, and input same goes for here, I times m plus j, right? And now we need to check what we are doing wrong here. So let me screenshot this kernel. So suppose you are in a warp. When we are in a warp, this thing will be constant. So let's consider I to be constant. But since we are in a warp, it is laid in such a manner that thread index varies from, let's say, we are at in some particular block and in some block ID, and only thread index X is varying from, let's say, 0 to 31 since we are in a warp, right? So how will input vary first? Let's check. For thread 0 in a warp, I will be constant, uh, M will be constant. We are adding J as 0. So the next element then we will access is IM plus 1, IM plus 2, IM plus 3, and up to IM plus 31. So the access from the input array is coalesced, right? All of these are consecutive memory locations in the global memory, and we can access the capability called DRAM burst as mentioned earlier. So the hardware will identify that these are consecutive memory location and it will send it in a block at once. But on the other hand, let's check output. So output goes by j dot n plus I, whereas j is varying, I is not varying in that case. So first kernel, first thread, it will be 0 plus I. For second one, it will be n plus I, then 2n plus I, then we have 3n plus I, and so on up to 31n plus I. So all of these locations in the output matrix are strided by n. So the first location is here, second location is here, third location that we are accessing is here. When we are arranging it is in a linear order, right? Since all of these arrays, input and output, are row measure arrays. So you will see while the read access from input is coalesced, the write operation in the output is not. What we can do? We can do something using shared memory and tiling. So we will load into shared memory as coalesced, as discussed earlier, and read from it in an uncoalesced manner. So I have written another kernel as well. Let's open that. Which one is this one? Let me take a screenshot of it. So instead of not using shared memory in the naive one, we are taking the capability and using the capabilities of using shared memory with a particular tile size. You will observe that we have added one here to avoid bank conflicts, right? Then we are again doing the same thing, calculating I and j. We are storing the ty and tx of a thread right now. Then we are storing the I comma j, like input I comma j element of input, which we can also say it like this, to the shared memory at this location. This is fairly understandable code because we have seen it multiple times, right? Now we are doing sync threads because we want all of the threads to complete their operation of loading their particular elements that they're taking care of in the input matrix to load it into the shared memory. And we need that they complete their operation before moving on to the next part of the code, which is this. Now we need to calculate the output indices in the output matrix. So you will observe that threads obviously will remain same, but the block index will change. So suppose in the input matrix we are at here, when it is transposed, what will happen to it? Let's say it moves to air, right? So we are swapping the block X and block Y with each other. So suppose this is uh, 1 comma 0th block, and when we swap them, we go to 0 comma was first block, right? So we are swapping that, but the element in the block that we will access, it will remain the same. So that is the ultimate understanding here. So you can write it using some numbers and check the calculation for yourself how it makes sense that we are swapping block X and block Y, but instead we are not doing it for the thread index as well. Now you will observe that we are loading into the shared memory coalesced patterns, right? So all of these I dot m plus j, they are coalesced together. We have seen in the naive one, and we are storing them in the shared memory. So the first step is done, that we are loading it in a coalesced manner, but when we are reading it, it is uncoalesced. So uh, let's check this one. So for thread 0, it will be this. And for thread 1, it will be this. For thread 2 or thread 31st, it will be this. You will see the ty is constant in all of them. So the column is constant, but we are changing the row. So this is the particular column, but we are changing the row. So the read access from the shared memory is uncoalesced, right? But we have seen that the read from shared memory is much faster, like 10 or 100 times faster than global memory's read, whereas global memory is much slower. So we took the advantage of tiling operations and shared memory to read it from an uncoalesced manner so that we offset the cost of reading it from the global memory. And the calculation of indices in output is fairly simple. Again, we are doing the same thing. We have I comma j, number of columns is n in this case. So out I dot n plus out j, and we are reading from the shared memory. And since we are swapping the indices, we, instead of doing smtytx, we are doing txty. So I hope that makes sense. So this was all about this video. I hope this was informative.